what's near-field thermal radiation? To understand near-field thermal radiation, you need to understand what does thermal radiation mean. Thermal radiation is electromagnetic radiation emitted by all kinds of materials found around us at temperature above 0 Kelvin. You know that all materials are composed of charges, positive and negative charges, and they are vibrating due to the thermal energy they possess. So if you consider one charge vibrating inside the bulk and see the radiation coming out of this charge, some of the radiation can cross the interface between the bulk and the vacuum and can have propagating waves. Those propagating waves can travel for good, can travel for very long distances. And those waves are the ones who comprise the thermal radiation we know in our engineering applications. And the black body radiation is just calculating how much the maximum the vacuum can support these waves. So there is another kind of waves that can exist. Those waves are called evanescent waves. As you see here, the waves cannot propagate along through the vacuum. They are just decaying away from the surface exponentially, and they are from the total internal reflection. So what will happen if you bring another body closer to the emitting body, very close to the emitting body? Then you will have the propagating waves and evanescent waves participating in heat transfer, and you will have an increased rate of heat transfer. So it is all the waves that can happen in the material. There is a third kind of waves that cannot propagate in vacuum nor in the bulk. They are called surface waves, and they are emitted by charges near the interface. So here comes the distinction between the propagating waves and evanescent waves. Far field thermal radiation, or the thermal radiation used for engineering applications, which we know is comprised of the propagating waves. If you bring separation distance very close between the emitter and the receiver, you will have the evanescent wave from total internal reflection and surface waves take part in heat transfer. So why is very interesting? The near-field thermal radiation is very interesting for engineers. You can understand or appreciate the importance of near-field thermal radiation from this dispersion relation. Dispersion relation is just a relationship between the frequency in space and frequency in time. And if you notice, it's comprised of dots. Every dot represents a wave state or a wave solution. The more the dots you have at any frequency, the more the heat transfer you will get. So this green area is the propagating waves that can propagate in the vacuum and in the bulk. The blue region is just from total internal reflection. And the most interesting ones are the surface waves, which cannot neither propagate in vacuum or the bulk. You can notice here that those surface waves has some kind of spikes. You see these spikes mean that there are many states to transfer the energy around this frequency. This is the one responsible for the spectral selectivity of thermal radiation. So now we understand what's near-field thermal radiation, why it's very attractive for engineers. It has three main characteristics. The first one, it has increased heat transfer than the far-field thermal radiation. It gives you a chance to control the heat transfer. If you manipulate the separation distance, then you can control the heat transfer rate. The third one, and the most interesting one, that it can work as kind of laser. Like you can have the heat transfer by thermal radiation happen around a certain frequency. And that's very interesting for applications such as thermophotovoltaics, which are a very new kind of engines or very new kind of energy converters that convert heat to electricity without any moving parts. The problem of these modern engines that they have low power density and they have low efficiency. So if you have your heat happening around a certain frequency like this, then you can boost the efficiency of those engines. And also from the increased heat transfer, you can increase the output power density of those engines. Second interesting application is for photolithography. Photolithography is one step in microfabrication. It happens with light usually, but the problem that the minimum feature you have is limited by the diffraction limit of light. For near-field thermal radiation, you can go beyond this diffraction limit of light. The third application very interesting is the heat-assisted magnetic recording that will enhance or increase the data storage intensity beyond what we have today. You know that most of hard drives are working by storing the data on a magnetic media. If you use heat with magnetization of the material, you can control very small area of this magnetization media to magnetize. So you can write your data on a very small area, as small as 50 nanometers. And one third application is for spectroscopy. When you heat the material, every single material have its own characteristic evanescent waves. If you are able to scatter those evanescent waves with an AFM probe and do spectroscopy for those waves, you can distinguish between many kinds of material.